All right, so now I'm going to talk about how to actually convert something to Smith normal form. So this is reduction to Smith normal form. Okay, so it's going to be similar in some sense to Gaussian elimination. So to reduce the boundary matrix, right, we will proceed in a manner which is similar to Gaussian elimination. Okay, so we move basically a 1 to the upper left corner, and then we zero out. It's like the rest of the matrix, right? So in at most two exchange operations, right? We move a 1 to the upper left corner. And with at most np minus 1 row and np minus 1 column additions. Right, we zero out the rest of the first column and row. And then once you've done that, right, so the basic idea, if you will, is that you have this matrix, and then you want to move a 1 to this thing, and then you want to zero out these parts. And once you've done that, right, you can sort of essentially remove the first row and the first column, and then do the rest that's like on the remaining piece. So there's sort of a recursion step involved here. Okay. All right, and then we can recurse for the submatrix obtained by removing the first row and column, right? All right, so that's a relatively straightforward thing. Okay, so we first call let this NP, which is eventually it's like going to give me the normal form operation, right? And then it's indexed by I and j, right? So this is going to be a ij, and then call the function with let's say x equals to 1, which is the position of the first diagonal element. Okay, all right. All right, so let me just erase the front part. It's like, and then I will write down the algorithm. So again, hopefully the idea is quite clear, right? You want to move a 1, it's like in the top left part of the matrix. And of course, you can do that with a a row swap and a column swap in the worst case. And then once you have that, it's like you can use these addition operations like you do in Gaussian elimination to zero out the rest of the row and the rest of the first row and the rest of the first column. Once you've done that, it's like you're left with a subblock. It's like, or a submatrix, which you get by removing the first row and column, and then you do the same thing over and over again. Okay. All right. So so it just returns a void, and then reduce x. So x tells you which row and column you're starting off with, right? So if there exists a k greater than equal to x and L greater than equal to x, right, with a non-zero entry with NP KL equals to 1, then you do the following. Okay, so if it turns out that whatever is left over in the subblock you haven't worked with is all zeros, then you stop, right? Because then you're already in Smith normal form. Okay, so the point is that if you're not in Smith normal form, then you take that entry, which is 1, and you basically move it, it's like to the ith position, x, x position. Okay, so if so, you exchange rows x and k. Oops. And you exchange sort of columns x and L. Okay. All right. So again, the conditional statement is that if there's at least one entry which is 1, right, then you swap that into the x row, x column position, right? Okay, so then what remains then is the following. So for I equals to x plus 1 to np minus 1, you do the following. So now we have this Gaussian elimination light step, which we want to zero out the entries. Okay, so if np I comma x is equal to 1, right? So if there's a non-zero entry in, it's like, then you want to zero that out, right? Then you add row x to row I. Okay, then you end if. Okay, so so again, it's like keep in mind that we're in modular 2 arithmetic, right? So if that entry is 1, you have to recall that the because of this row and column exchange which we have, it's like that entry at the xx position is now 1. Okay, so if I add that row, right, to the ith row, that will zero out that 1 there, because 1 plus 1 is equal to 0 modulo 2. Okay, so that's how this is zeroing stuff out. Okay, and then you end the for statement. So what this will do then is that it will zero out, that entire, that entire entry. Okay, so you can do the same thing for j equals to x plus 1 to np. You do the following. Right, so if np x comma j is equal to 1, then you add column x to column j, and then you end if. Okay, and then end for statement. Okay. All right, so once you've done this, all right, so again, it's like, let's try to break this up. What's happening is that you try to find, you look at this subblock, it's like of things which you haven't yet worked on. You see if there's a non-zero entry. If there's a non-zero entry, it has to be a 1, because we're in modular 2 arithmetic. We swap that into the top left corner, right? Once you have that, you can then easily add, it's like that entry either in the row or column sense, right, to zero out the rest of the rows and the rest of the columns. Okay, so that's what these two things do. Then once you've done that, right, now you're in a situation where you have now a bunch of ones, right, potentially, and then zeros here. Okay, and then there's this block you have to work with. Okay, so you recurse, it's like on this block now. Okay. So you reduce x plus 1. Okay, and that's really all there is. So it's a relatively straightforward algorithm in the modular 2 case. It's much more involved. It's like if you're using integer coefficients. In particular, it's much more involved to prove that this actually converges. But in modulo 2 arithmetic, it's relatively straightforward. Okay, so what this tells you is the following, right? So we have at most so let's do the algorithm. So we have at most np minus 1 row and np column operations per call. And hence at most np minus 1 plus np times the min of np or np plus minus 1 row and column operations. In total. Okay, and then of course you have to multiply it by the length. So the running time looks something like big O of np minus 1 times np times the minimum of np minus 1 np. All right, and then the amount of memory, it's like you have to work with is about np minus 1 plus np squared, right? To store the matrices. Okay. So more or less, it's like what this tells you is that, so this says that the reduction to Smith normal form of the boundary matrices right is at most cubic in time. In memory, and at most quadratic in the number of simplices. Sorry, in time. I'm sorry, that's not what I meant. Okay. Let me just rewrite that. most quadratic in the number of simplices in memory. Okay, so this gives you sort of an upper bound for how long these kind of operations will take. Okay, so let me just stop here for now.